Hi, I'm Sean Cribbs. I work at Comcast Cable, and for the last 9 months or so, I've worked on a project where we built a piece of HTTP infrastructure using nginx and Lua, and that's what I want to talk about today. So, to give you an introduction to what this system is about, I need to give a little background. So, Comcast has a big infrastructure. For those of you who don't work there, I see a lot of my coworkers in the room, which is nice, but some of you probably already heard about this before. A lot of our products and our services rely on internal APIs. We have around, at my last count, 400 APIs that service various aspects of the business, from things like working with consumer products, the mobile apps, the set-top boxes, the Wi-Fi gateways, all of those things, as well as internal uses for billing, account management, customer service. So when you call in the call center, there's probably some customer service representative who's using some of these APIs that give them information about your account and the services you've had before and all that relevant information. And then there's also partners. So other MSOs that we are providing, sorry about the TLA there, other cable operators that we are providing our technology to in a partnership or relationship, or content providers, so people who are giving us streaming content, they interact with us over APIs as well. And so we need ways to protect and manage all of these different surfaces that we expose. And that's what API management is about. So when I talk about API management at Comcast, and this is a term you may have heard in the industry, is there's some buzzwords, there's some startups that have API management products. For us, at Comcast, this means primarily two things. Is access control and capacity management. So access control is this caller who's asking for some service to be provided from one of our APIs. Do they have actual access to this API? Has the service owner said, yes, this application, this consumer can call this API? And then capacity management is basically, how do we protect those services from being overloaded? How do we give a reasonable fairness to all of the callers? Most often in the industry, this is called rate limiting. But we'll talk a little bit about how we're doing that differently at Comcast. So this is something we've actually had for a while. And the old system was called Code Big 1. So I don't remember, because I wasn't even here, right, at Comcast. I don't know why it was named Code Big. I guess it was like dream big and dream with code, so you code big, something like that. But it's that internal name for our API management project. So my team that I've worked with for the last 9 months has inherited this existing infrastructure, which we call Code Big 1. We started building Code Big 2 maybe about like 18 months ago. So this original Code Big 1 was built around 5 years ago. And it looks roughly like this. You have an API consumer, and hopefully this diagram won't be too surprising to you if you have any idea about what API management does. And then that API consumer, when they make a request, that request goes to a CDN. That CDN provides us the ability to traffic shape, so basically to route requests to different parts of the country where our various data centers are, as well as caching. So some of the APIs required that some responses that were expensive to produce could be, time-limited cached. The CDN would provide that, and also distribute that cache around to different POPs. So after it passes through the CDN sends it on to what was our vendor's API management solution. And this does those two pieces that I talked about before, the access control and the rate limiting. And some of this was on the internet, like in the cloud. Some of this we had on premises. So some of it was in our data centers, some was outside. And once the request has been authenticated and it's determined that it's not over the rate limit, then it would be passed on to a load balancer. So everything you've seen so far is probably on the internet. And when you reach the load balancer, that's the edge of Comcast's network. The load balancers were they use a VIP within a single data center. They had some DNS round robin to different data centers. And so it's not like a physical piece of hardware, but more, networking goop. And once it passed through the load balancer into Comcast network, the first thing it would hit is an IAuth, so an intermediary authentication server. This basically provided a gateway into the origin services. So we've already determined the request is okay to come through to Comcast network. Now we need to make sure that we're receiving it from the correct people, and that's what the IAuth does. In addition to acting as that kind of DMZ machine, it would also take the incoming request and rewrite it to the individual hosts that are sitting behind it. This is a major piece of the infrastructure. And then finally, you get to the origin APIs. So you see you've gone like 5, 6 hops to get from the consumer all the way to the origin API. What are the different challenges that we had? So first of all, given the size of this system, we had a lot of problem with visibility. The CDN and the vendor API management solution, their statistics, their instrumentation, that information came to us very delayed. We had a lot of problems knowing when there was a production incident, well, was it the vendor API management solution? Was it the CDN? Was it something on our side? So we just really didn't have visibility. And it's kind of hard to be on a support call and somebody's like, what do you see from the code big end? I'm like, I don't know how delayed these statistics are. They may be 6 hours old, so I can't really help you. That was really frustrating. And then, related to that was responsibility. It's super easy to say, oh, it's the vendor's fault, which is doesn't promote a real healthy, development and support culture, right? And it also makes it hard to do the right thing by the users. You actually, when you get on that call, you want to resolve the problems, right? So you don't have to encounter it again, and so the business isn't impacted. And this kind of support rodeo is really, really frustrating. So we wanted to resolve that issue of responsibility. And then there's scope. If you could, that diagram was incredibly simplified from what it actually was, but there's a lot of moving parts. And if we could reduce the number of moving parts and the number of features we didn't use from the vendor solutions, we'd be better off. And then from a technical standpoint, super high latency. If we have quite a few API consumers who are inside Comcast. There's no reason why they should go all the way out to the internet and through 5 steps to come back into Comcast network. They could just go right across the network in the same data center even, potentially. And then just the vendor API management solution is a multi-tenant thing. We may be competing for resources with other customers of theirs. And so we would have very variable latency. And then finally, it's not always secure end-to-end. There are pieces that went in plain text, and given that a lot of our APIs transmit personally identifiable information, it's incredibly important for us to make sure that those channels are secure. So if we were going out to the internet through who knows what machine, that we don't have control over those hops, that was a challenge. Okay, so this brought us to CodeBig 2. We decided to bring this in-house to hopefully alleviate a lot of these issues. We had a goal of simplifying the architecture, so reducing the number of moving parts, making more constrained choices about what features we need from the previous solution, and then just trying to make our own jobs easier. We definitely needed increased visibility. So having control over the machines that run this, but also having instrumentation built into the system was really important. And we wanted to use open source tools. There's lots of great vendor software out there, but we felt like there's also lots of great open source software that we can use. So what does the architecture look like? Well, an API management system is basically an HTTP proxy, right? But what's in the middle of that is some custom logic to decide, is this person authorized? And have they met their rate limit? So there's a really elegant solution to this problem, which is, you probably know the answer, which is to use nginx, which is already a great reverse proxy, and the embedded Lua module. So there are a number of reasons to pick Lua. The reasons to pick nginx are obviously it has really great performance. It has a great open source community. The aspects of operating it are really well known. And for Lua, it's designed to be an embedded language. And a lot of high-performance applications, including games and other sorts of infrastructure software. So I actually heard rumors that there are some various operations products you can buy that have Lua embedded, which is a good thing. So, how do you actually go to build this software? What does this look like? Well, the Lua Engine X module has various extension points within it. So these are directives you can put in your Nginx configuration file to inject Lua code into the request response cycle. So there are two extension points that happen on startup. So the Nginx server starts up, it forks its workers, those workers initialize. So those two, init and init worker. And then you have various spots where you can inject your own functionality during each individual request. So the directive in the configuration file is basically you take one of these phase names and you add by Lua or by Lua file or by Lua block. Incidentally, the OpenResty folks who wrote this module are deprecating the first one. There's problems with like escaping quotes and whatnot in configuration files, so use the block. It has curly braces. You don't have to escape anything. Or you call onto a file, which we do some of both. Okay, so we have all these extension points. What will we actually use? In CodeBig, we only use 4. So we use the init and these 3 per request phases. So flowing from right to left is, and here comes my arrow, flowing from left to right is the flow of the individual requests. So it has access first, and then header filter, and then log. So in the init phase, what we do with CodeBig is we load our code. So we actually require the Lua modules into the server, and then we ask it to load the API configuration in memory. So we have each individual API endpoint that's for that specific Nginx server will be described in a JSON file that we can load in and then use that to determine how we do authentication and all of those things. So then when a request comes into one of those endpoints, we hit the access phase. And this is where we do authentication. So we do both OAuth 1 and OAuth 2 bearer tokens. Basically we validate that the request is okay, that that particular user is able to access that. Then we do our rate limiting. And then finally we apply any upstream tweaks to the requests. So one of the things that was interesting about transitioning from CodeBig 1 to CodeBig 2 is that there are all these hidden features, especially in parts of our infrastructure like at the IAuth layer that we didn't know people were using. And some that were like in little text boxes hidden away in the vendor APIM's solution that we realized, oh, that's really important to someone, we need to replicate that. So there are some aspects of we fix up the request for the upstream service before it passes on. At this point, this is where, after it passes the access phase, this is where we proxy to the backend service. So you see we only really had one step to pass to the backend service. And then in the poorly named header filter phase, we tweak the response as it comes back. So we don't touch the body of the response, we just add and remove headers or transform them in some ways. And then finally in the log phase, this is where we clean up. We release the capacity, or we do the accounting that we needed to do for the rate limiting, and then do some cleanup tasks related to that request. The nice thing about this is these phases ended up, and this wasn't the case when I gave a version of this talk last fall, but these ended up being reflected in the way we structured our code, which turned out to be pretty nice. So this is basically the implementation of what we've called a plugin. We don't really have a better name for it, but it's basically a module structure and an object structure. And I hope that that's big enough for you to read at the back, but I'll describe what's going on here. So in each functional vertical of the code, so single responsibility like authentication or capacity management or request and response tweaking, those each are structured as a plugin. And those plugins have specific methods that refer to the individual phases that they'll be called in. So in this case, we have like the access phase. We have a post-access phase that isn't actually a callback from nginx, but that we call after it says, yeah, you can go ahead and process this request. So if they need to, this is, for instance, used by the request tweaker that adds headers or query parameters or whatever. And then there's the header filter and the log. An interesting thing to point out about the Lua language here. So if you are familiar with JavaScript, I imagine many of you are, like me, this will look pretty familiar. You're basically building an object using typical prototype inheritance. And you'll see all of these bits that make that inheritance work in the new function here. So we create a new bare object in Lua. They're called tables, just a key value structure. And we've taken the parameters in the new function and are sticking those as members of that table. And then we define a new member of the table, super, to be self. So this is where when if you access the super member of this table, it would point to the module that currently defines that function. One of the things you don't see here is that actually the colon versus a period in Lua tells you, oh, well, the self parameter is implicit at first. So you actually have more like Python object methods, but you just can sugar away the self at first. Anyway, so then the set meta table says, when I go to look up a method to call, where do I look? And that says that, so this module is the meta table for the object that I'm returning, for the table that I'm returning. Sort of like, we're like setting the prototype on the JavaScript object. And then finally, the index is, how do I find names on this object? It's sort of a thing that's really hard to explain about Lua's object model. But that basically also has to do with how do you find members of the object. And finally, you return it. So this is a really simple structure. How do we apply it? Well, our top level code, our access phase, loads and initializes each of these plugins that each endpoint has configured. So say for this, for endpoint A, I want to use OAuth 1, and I want to use client rate limiting and host rate limiting. Okay, so those will be listed in its configuration as the plugins to use. And it will require the file and call new on it and pass all the information. So that's the first line, says local plugin, and passes the information from the request context and the configuration into that plugin. And then we go through and check, does this plugin actually allow you to pass? So this is where it calls and does authentication. So if it's the OAuth 1 plugin being called, we call the access phase on it. It says, is this request, valid? Does it use a valid key, and was it, signed properly? If it's not okay, we just bail. So if any of these components wants to deny the request, we say, exit. The plugin decides what error it should be, 401, 403, whatever. And then, for the example, in the rate limiter, it would be 429 for too many requests. And then we exit. So none of the rest of this code will be processed if any of those plugins doesn't accept it. And then finally, if it does, then we insert it into the list of things that will be used later. And then at the bottom there, say, well, we'll call the post access. Since all of them succeeded, let's let them do their other work. And then the rest of the phases, like the access phase is the most complicated one because it's setting everything up per request, right? The rest of them just look like this. Oh, hey, we're in the header filter phase. Get me the plugins, loop through them, call all of their callbacks. So this is a really nice structure. And this is reflected in the configuration file too. So the first line we just say, where is our code going to live? And for various reasons, thanks to the RPM package management, it tells us to put them in user share. Whatever, I would have done user lib, but so that defines a way to look up files when you say require codebig. It's going to look at user share codebig init.lua or user share codebig.lua. And then we define some shared memory. This is basically a concurrent dictionary that's shared between all the nginx workers. We use this for accounting information. And then when we init each worker, or init the whole server for that matter, we require the codebig code. So this is going to find one of those files that we saw on the first line. And then we give it the path to all the JSON configuration. So it loads all that stuff into memory, like I said. Then for each individual virtual host, for each endpoint basically, we call those individual phases. We say codebig access this host and header filter and log. So there's a nice tie between what's written in the config file and our code. And the best part about this is about 3,000 lines of code total in all of codebig. So we recreated all the features that we used from that vendor, which we have no idea how much code they have. Probably a lot because, you know, it's a big project. And we did it about 3,000 lines of Lua. And there's about 1,000 lines of Python as well to manage our configuration, and probably an equal amount for our functional tests. But that includes 2 authentication methods we use, plus a third one that's a work in progress. The capacity management, and like I said, the handful of unexpected features we needed. So, of course, there are other pieces of this puzzle than just the API and proxy, so let's talk about those. Within a single data center, our architecture looks sort of like this. We have a VIP at the edge of the data center, so this is a virtual IP, right? And then we have a number of HA proxies that can claim that VIP. We're currently in a master standby type of situation, but we could do a round robin if we wanted to later. So we basically have redundancy at the load balancer level. And then those HA proxies proxy to various nginx machines. And these run the codebig code inside them. And then finally, of course, that proxies to the origin API. So we still have a number of moving parts in here, but this is all within Comcast's network. The best part about this is because of our load balancing scheme and the high performance of nginx, we can have really low downtime on upgrades. We can just reload the server if we want. We're a little bit more careful about that because we haven't extensively tested it, and we haven't needed to extensively test the like live reload thing, because we can just turn off one of the nginx machines in HA proxy, reboot it completely with its new configuration, turn it back on in HA proxy, and do that in a rolling fashion without any loss of capacity, really. And the nice thing about this is also is that it gives us a separation of concerns. So we can scale each of these layers independently. If we need more load balancers, we can roll those out and change our VIP scheme from pinned to round robin. If we need more nginx machines, which we actually have grown those at one point, we can add more. So how do we actually make our APIs redundant? We do have all this capacity in front of them to protect them and to load balance, but they also live in multiple data centers. So we would really prefer that customers and partners who are on the West Coast go to somewhere on the West Coast instead of here to Philly. So what we can do is we say we can configure each API for multiple data centers, and even potentially customize what the services that's being proxied to per data center, and then give the consumers choices about which endpoint they'll call. So we did this with some clever DNS, as you can see on this. Basically, we create an authority record, an A record, for every VIP that points to a codebig cluster. And then for every API, an instance of that API in that data center is a CNAME to the VIP. So if I have a service that's running here in Philadelphia and I want to make sure that my calls are local, I can use that CNAME that points to my local data center, which is really good. Or if I don't care, but I want to prefer, or rather I want to prefer one, but possibly use the other if this one's down, I can use this FO, which uses a health check and can prefer one DNS name or the other. And then finally, you can give the simple one, which is like, I don't care where my requests go. They just need to go to any one of these instances of this API, and you can use the simple one. So in this way, we can do sort of some of the complicated things of routing and load balancing just from the client side, which is nice. Okay, so how do we do capacity management? I mentioned we do it differently than what is the prevailing notion in the industry. And this is the part where I always like to invoke our VP, John Moore, who loves this equation. So let's look at a couple scenarios, and we'll evaluate them with this formula. Does anyone else know this formula? And people who are in John's department can't answer. No? No, okay. So this is a form of Little's law. Let's talk about what it means. So n is the number of concurrent requests. So we're talking about how fast do requests come to a system, how many are in flight at once. And keep in mind these are all averages. All these figures are averages. X is the transaction rate. So how quickly are they coming in? Like this is what in the industry people say, yeah, you get 5,000 requests a minute or whatever. If you've used Twitter's API and been denied, you know about this number. And then finally is the response time. How long does it take for the service to return you something? Okay, so what this means is if we have a high transaction rate and the response time is constant, we're going to increase the number of concurrent requests, right? If the response time goes up, we're going to increase the number of current requests. If both of those are low, so like you have a high performance service and low traffic, then you have a very low number of concurrent requests. So it's a pretty intuitive formula, but unless you'd encountered it before, maybe you hadn't thought about it. So again, this is Little's law. So let's look at the scenarios I mentioned. And this is a really anemic web service, so the numbers are small so you can comprehend them, not so they're actually realistic. Let's say you have a client and it's sending requests at about twice a second. And the origin service is responding about 1 second per request on average. So this means that basically you have 2 concurrent requests in flight at any time. So what happens if the origin service starts to respond with 10 seconds? Maybe they're having an incident, maybe they don't have enough machines, whatever reason. Now you've got 20 concurrent requests. You've gone up an order of magnitude in terms of the number of requests being serviced at once. And maybe, obviously the numbers are low, nobody should fall over with this, but maybe that means that like everybody gets an incident, right? So what we realized is we can't really control the response time and the origin, nor should we have to, because that means we get to be the mean people that say, your service is too slow, or your service can't handle the capacity that you're allowing. And we can't control the request rate at the client, at least not as easily. We don't know how fast they're going to come in. We can tell them go away, but that's the best we can do. So really the best solution in our mind is to control the number of requests in flight, which is actually really simple because remember that shared memory I said that we use for accounting information? It means that when a request comes in and we say, yeah, it's okay to let it go, we increment a counter. And then when it finishes, we decrement a counter. And in that access phase, we can say, well, have they exceeded their limit or are they at their limit? If they are, then we can reject the request before it even goes to the origin. And then, this makes it a lot simpler to manage capacity. And in a lot of ways, if you can understand how many concurrent requests the origin API can support, that also makes it easier to provision new clients. And then we can average that capacity over all the nginx nodes we have in each data center. So this means that also we're very resilient to fluctuations in performance. Like if the service gets slow, we know we're not going to be sending it more than it can handle theoretically. If the clients pile on, then we're going to turn them away before they overload the service. So it's really, really nice in that respect. A little bit about deployment. We have many data centers to deploy to. We currently use Ansible, partly because I don't remember the reasons, but it's actually really simple to understand. But basically, our workflow looks like this. Ansible runs commands over SSH. That's all it does. You can put those commands in sequences in what they call playbooks, and we store those playbooks down there in the center in our Git repository. We also store the configurations for each API in another repository. And so when we get the templates for what the nginx config looks like, those API configurations and the secrets, so in the case of OAuth 1, there's every key has a secret to use to sign the request. And for various other things, like for our bearer tokens, there's some keys that we need to decrypt them. And those are all in the version control system. We pass it through our generator, which outputs, excuse me. it outputs a configuration file for the entire nginx server, one for the VIP, so the endpoint within each data center, and then the various configurations for the virtual host, so tying the name of the virtual host to the JSON configuration. The JSON configuration contains all the stuff that each API needs, so like its keys, where does it proxy to? Actually, no, that's in the nginx as well, but what authentication methods does it use, those sorts of things. And then Ansible takes those, combines them with the playbooks, and redeploys the nginx. If we need to build a new cluster, a lot of our stuff is on OpenStack, so we have Ansible deploy that too. Now lately, we've actually transitioned to running a lot of these automatically with Jenkins, because we realized this is kind of a waste of our team's developer time to sit there and deploy 10 data centers from their laptop. So we're working on better ways to do that, but right now we're using Jenkins. So what do we get from this? What are the results? Well, one of the things that I mentioned, it's high performance. So let's take a look. This is an API. This is a graph of some statistics from an API. And this one is used by all the X1 set-top boxes, as well as some of the mobile and web on-demand apps. Basically, it's an API that determines whether a customer can see a particular piece of content, whether it be an on-demand program or a channel or whatever. I think it's mostly on-demand. But anyway, it's probably the single highest traffic API in our entire infrastructure, and it's the one we converted first. So what you can see here is that when we switched over, this top red line is the 99th percentile response time, and it dropped quite significantly. And the blue and yellow lines are the average and the median, respectively, response times. And so you can see that the mean before is the new 99th, which is a big improvement. And then the mean itself dropped by a factor of 10. So we've gone from around 200 milliseconds down to 20 milliseconds for latency, which is a really big deal for them. Additionally, we achieved a lot of stability. So how I told you about when it's going out through the internet and who knows what machine and the CDN and all that, and we still do some CDN stuff, but it's less so now. The latency could really vary because we don't know what machine it's going to go to, how many hops it's going to have to jump through. So this is a graph of the maximum response time from a service that is used for personalization. So tracking customers' favorites, like what's their favorite shows, what resume points do they have on on-demand videos, what are the things they most recently watched. So stuff that we use for both improving the customer experience as well as just front-end features. So here you can see there's a big cliff there, right? This is the median latency for their service. And you can see it goes from wildly variant and all over the place and super high down to really consistent. Very stable after the switchover. And I think this is my favorite one. And it doesn't look like much. It looks like, what is this crazy graph, Sean? What are you showing them? This is a graph of the latency that our nginx and Lua code adds. So this is basically what was the time that we started the request, and what was the time, and how much time did the total request take, minus how much was the time that the backend responded. And what you see here is the yellow line is the maximum, and on the left are seconds. And then there's a faint blue line, which looks like the axis, but isn't, and that's the 99th percentile. Basically, with the measurement we have inside nginx, you can't measure the 99th percent. It's at 0, effectively. So it's sub-millisecond. Whereas the maximum of this graph, let's see if it'll go. Where is it? Okay, so that's the 99th on the bottom. The maximum is actually, below 200 milliseconds, but averages around 50 milliseconds. Most of it is sub 50. So that's really good. So in terms of successes, like I mentioned, that first big API that was on CodeBig 2 saw the previous median latency become the 99th. That's a really awesome story to tell. We're now hosting around 400 endpoints, which is more than what we were hosting on the vendor before. So even as we were converting people from the vendor solution to ours, we had new ones coming on. And then I did, and this the Splunk team will probably be angry at me, but I tried to do this week-long query of how many requests we did. And I decided, oh, this is taking too long. I'm going to query one day. So I measured on Easter Sunday, we did 367 million requests, and that's a light day. This comes out to about 4,000 requests a second, which you think, oh, that's not actually that big across 10 data centers. It isn't, but that's a light day. So if you think about how much, in addition to the performance that we're getting for everybody, how much money we're saving not buying that vendor solution when they charge us per request is really big. And then finally, this is a great story, and I can't tell too much about it in detail, but we prevented a major outage in February. So there was a network blip you might have been aware of, especially if you're a Comcast customer. In February, we had wide-scale problems across multiple parts of the infrastructure. And then people were like, oh my gosh, is my cable out? So they get on their My Account app on the phone, like, is my cable out? Is my cable out? Is my cable out? And so this meant that this one service that sees a pretty consistent traffic across most days had this huge spike. And what we did was we actually prevented that service from going down because a lot of customers got, oh, I can't check that for you right now, which is not great, but we did prevent the business from having more catastrophic effects happen to it. So we did have some challenges building this. The first one I'd like to point out is that finding quality Lua libraries for use inside nginx is kind of hard. Some of that is just the community is really small. Some of it's that a lot of game developers use it and don't share their code. And some of it is just that we didn't know where to look. Luckily, the OpenResty folks who wrote that Lua Engine X module are working to improve this. There's also a package management repository called Lua Rocks now. So we'll be looking to probably integrate some of that in the future. And then our conversion schedule demanded that we delay building a self-service API. And this one is kind of painful to me because right now it's all tickets. And nobody likes tickets, right? So what we have to do is when somebody wants access to an API or somebody wants to deploy a new API, they have to write a ticket to us and we have to talk to the appropriate people and then set it up. Luckily, once we set it up, because we have the automated deployment, if it's ready, it'll be ready within half a day. We do have plans to build that this year. We're thinking about actually using Lua for that as well inside nginx, which would be fun. This one is a bit older, but we did have a problem with nginx configuration file size. So we were generating these configuration files, right? And then nginx had this kind of well-known but hidden to us limit on how big the files can be. So it would get to, I don't know, it was 4 megabytes or something, and then it was nope, I'm not going to parse anymore, see ya. So what we had to do is, because previously we were generating our configs into the nginx file, so all the API information. We moved those out into Lua files that we generated, and then we decided, oh, well, we only have templated Lua files, that's kind of crazy. Let's move it out into JSON, which we know we can produce consistently. And then, of course, if you're running a high traffic service, you get to get intimate with the kernel and tuning the TCP stack. So as we got lots of connections to that API that I mentioned that had the huge performance increase, we basically had to turn on the flags that let you aggressively reuse and expire sockets. And this is mostly because, although we are running an HTTP 1.1 stack, a lot of the clients just call once and then disconnect, which is hell on your TCP stack. And then finally, owning availability, even bringing it in-house. We discovered that we have to integrate with lots of systems that other people run. We have to interact with them, and environments that have their own practices that weren't ours. So we have to balance how much of the operation we and deployment that we own, and we've had to work closely with people to overcome some institutional issues and technical ones as well. So finally, I would say if you're building any kind of HTTP middleware, definitely look at nginx and Lua. The LuaJIT interpreter is amazing. I looked at the Lua languages, I was like, God, there's no way this is fast. They made big strides in JavaScript, but Lua is actually way simpler than JavaScript, and it's got a great JIT. It gives you good performance and flexibility. Build an automated deployment pipeline. If you want to stay up like we have to be, we want to be the least interesting part of the infrastructure. So we want to be hands-off as much as possible. And we've been pretty successful with what we have so far. Again, concurrent request limiting is an interesting way to think about API management, rate limiting. If you're doing any sort of rate limiting, think about this instead of trying to count how many times somebody called in the last second. And basically it achieves the same effect with cheaper accounting practices. And then we built a network architecture that has operational flexibility. We can do lots of things without impacting people, and that's really powerful. So thank you, and I'm happy to take questions.
Hey, just wondering, how do you manage like analytics and reporting on the APIs that go through your gateway, and how do you deal with like managing performance and SLAs and alerting, that type of thing?
Okay, so the question is about analytics and tracking performance of APIs. Yeah. Is that correct?
So if you want to like segment, get reporting on which users are pounding on you the most.
Yeah. So what we do is we currently are sending all of our access logs to Splunk. And there are open source ways to handle that too. The elk stack, whatever you like. But we already had Splunk installed. And what we've done is create a set of indexes that let people figure out, and we open up this data to everybody inside the company who wants to have access to it. We're more familiar with the field, so we're usually doing the queries ourselves. But all those graphs I showed you were from Splunk. So we send all of our log lines. It contains a lot of information about each request. So like, what was the client ID of the caller? What was the path that they called? How long did the request take? What was the backend service that was called? What was the nginx host that, and it just goes on and on, including things like how many concurrent requests were going, which is a nice thing to report.
Could you speak a little bit about how you came to the decision to use Nginx and Lua? Were there other technologies you looked at? Like, how long was that process? Yeah,
this decision was not mine, but I will speak about what I know. We did look at the JVM. We have a number of Scala projects actually in the department, and as I understand it, it was just, in terms of performance and simplicity, the clear winner. There were a lot of things that we would have to build ourselves. We would have to pick a Java web server, potentially. Maybe we'd just use one that everybody else is using. I don't know. But the performance benefit and the small amount of code, I think, is a clear winner for this project. I mean, I'm speaking from personal experience, not on the sake of the team. I would have been like, yeah, I've been doing Erlang for 5 years. Let's use Erlang because I know how to run it. But this was also, Lua from a culture and a familiarity point of view is really similar to JavaScript. It's not a big deal to bring somebody on and let them learn it. Versus, hey, you have to learn how to write concurrent programs. That's a little bit harder to sell, right? So Nginx also just super solid technology. And every time I've used it, I've been happy with it. So,
I'm curious. You mentioned that you are rate limiting by blocking after you receive a certain number of concurrent requests.
Yes.
How does that work when you scale out the number of nginx servers that are doing your middleware?
Yeah. So this question has come up before, and I'm glad you asked it. We don't share any state across Nginx instances, only among the workers on the same Nginx server. So what this means is, we're going mostly by averages on terms of how many concurrent requests are going. And, the rate, the Little's law is based on averages, right? So we said, it's probably going to be okay, and in general it has been, that we just divide the number of available concurrent requests across all the Nginx machines. Honestly, we're over-provisioned. So it's not been a problem yet, but that is the technique we're using. We have looked at, say, like using in-memory key value store to track that stuff, but then you're adding latency, and we really didn't want to factor that in until there was an actual necessity. Any more questions? All right, well, thank you. I'll talk to you after if you want. Thanks.